Okay, my presentation is about analyzing the dynamics of fluid injection in a confined geometry. I'm PhD student in chemical engineering department and manager of a complex fluid research laboratory under supervision of Professor Seyed Mohammad Taghavi. And my project is supported by Petroleum Technology Alliance of Canada and also other organizations. In this presentation, first I introduce the general overview of the project. After that, the experimental setup and procedure are explained, and then I will show some results, and finally the presentation ends with a brief summary and conclusion. So fluid injection has several applications in industry, like plug and abandonment of oil and gas wells, food engineering, additive manufacturing, coating, and polymer extrusion. Actually, the fluid injection, as you can see in these pictures, has several applications that the fluid is injected in different environment, like a confined geometry, like into air or on a surface or in an immersed environment. So the main motivation of my study is application of injection fluid in plug and abandonment of oil and gas wells or P&A operations, which is the last life stage of oil and gas wells, in order to avoid reservoir fluid migration, as you can see in this picture, to upper levels and avoid contamination of water resources, and also to avoid casing corrosion due to oil and gas leakage. I'm going to show you a movie about plug and abandonment operations. Usually in these operations, we inject cement slurry. Here we have a oil well that the water is produced as an unwanted phenomena, that we are going to avoid water production through oil wells. So you can see the production of water through the oil wells. That is an unwanted phenomena. So to avoid the water production, first we set a mechanical plug in the production zone, and then the cement slurry is injected into the environment to replace the water and to actually avoid water production through this well. So motivated by this procedure, I'm gonna study the injection of cement slurry in this procedure. As you can see, in this schematic, the cement is injected on a bridge plug to replace and remove the water and to keep safe the well from production of unwanted water. This operation is called dumbbelling method, as a dumbbailer has a cement slurry. So here you can see the dimensions of real dumbbailer and also the flow and fluid parameters in an industrial case. That is, here is the velocity of cement slurry, the range of density of the cement, the density of water, the in-situ water, the viscosity of cement, and also water, and also the rheology of the cement slurry in the industrial cases. So in this study, as you saw in the previous slide, we are dealing with a heavy fluid injection in a closed end pipe to remove light in-situ fluid. And the ideal situation is to placing a pure cement slurry in the desired area with a minimum mixing and also maximum in-situ fluid removal. So as you saw, there are several variable parameters like fluid properties, such as density, viscosity difference, and non-Newtonian fluid. About geometric parameters like diameter ratio, aspect ratio, inclination of the well, and eccentricity of the baler. And also about flow parameters like injection flow rate, heavy fluid velocity, and pressure drop. So we have defined several objectives based on these parameters that are buoyant injection of heavy fluid in an inclined closed-end pipe, investigating the effect of viscosity ratio, injection height, inclination, and injection rate. Also determining the impacts of non-Newtonian rheology on flow behaviors, like studying the viscosity ratio, shear thinning, and yield stress effects. And the main objective is to propose strategies for enhancing cement placement in plug and abandonment operations. Here you can see the dimensionless parameters that are involved in the dumbbelling method. We have around 11 dimensionless numbers like Reynolds number, foot number, Atwood number, Bingham number. We have two aspect ratio, two diameter ratio, and viscosity ratio, inclination, and power index. So in this slide, you can see the schematic of my experimental setup that I'm working on. That this setup consists of two pipe, two transparent pipe, an inner pipe for injecting the cement slurry, and an outer pipe to hold the water as which is a representative of the well. There are two reservoir, one for injecting the heavy fluid and another one for hosting the in-situ fluid. We have also several measurement tools like flowmeter, high-speed camera, rawometer, densitymeter, and we are using some non-intrusive methods like laser-induced fluorescence. Here in this table, you can see the dimensional parameters in our study, and in all of my experiments, the injection fluid is a heavy fluid, and mainly it's heavier than in-situ fluid. So in each experiment, first I fill the outer pipe with the light fluid, and as soon as I open the gate valve, the heavy fluid comes inside the outer pipe and remove and displace the light fluid out of the system, and simultaneously the camera and flow rate capture the image of the flow and flow rate and transfer it to the computer. So as the preliminary results, I want to show you an experiment that the heavy fluid is entered the flow domain, and you can see we have a jet structure at the first stage, and then a mixing region is created, and then the heavy fluid slumps on the lower wall of the pipe, reach at the end, and comes back toward the outlet. So as you saw, the flow is highly dispersive. We have defined different flow regimes, as you can see, the jetting regime and mixing regime. And then the front slumps on the lower wall of the pipe and also turns back toward the outlet. So you can see we have plotted the time versus x that the flow comes into the pipe, and we have this jetting and mixing regime. Then it slumps on the lower wall of the pipe to reach the end and then turns back. So we have published these results in Physical Fluid Journal. In this table, again, I show you the dimensionless parameters. The highlighted parameters are the parameters that we have studied until now, and we are working on these three parameters: Bingham number, viscosity ratio, and power law index. So I'm going to show you the preliminary results on the ongoing study about injection of a non-Newtonian fluid. So in this slide, you can see I used a shear thinning fluid, which is a mixture of xanthine gum, glycerin, and water. So you can see we have prepared three different solutions with three different rheological parameters. In these snapshots, you can see that from top to bottom, the viscosity of injection fluid increases. And you can see as the viscosity increases, the mixing between two fluids decreases, and we have a sharp interface between two fluids. And for the effect of inclination, you can see we have changed the inclination from horizontal to near vertical. And as the inclination increases, the heavy fluid detaches from the rest of fluid, And also in the horizontal configuration, the front of the fluid stops flowing. These are the phenomena that we saw for the first time, and we are working on them to quantify these parameters. We also used a yield stress fluid, which is a solution of carbopol, glycerin, and water. Again, we have used a raw meter to measure the rheological parameters of the fluid. Here is the graph for the fluids that we have prepared. That is the shear stress versus shear rate, and you can see the different yield stress of the fluids. So as a result of yield stress fluid, we have found three different regimes like breakup, coiling, and buckling. In the breakup regimes, you can see that the non-Newtonian fluid, when it comes inside the confined geometry, which is full of water, the light fluid is water. You can see in low flow rates, the fluid at a point breakup occurs. If we increase the velocity of this fluid, the breakup does not occur and the fluid starts to coiling around the pipe. And if we increase more the flow rate, because the pressure and stress in the system increases, the buckling of the fluid occurs and the inlet area is blocked by the heavy fluid. So these are the results that we have seen for the first time. As a summary and to wrap up the presentation, actually we are aware of environmental issue of unplugged wells, and we know that P&A operations deals with plug placement flows in confined geometry, and the objective of our study is to improve the plug placement flow in P&A operations. And we have found that mass mixing occurs near inlet boundary. We can have more stable interface by increasing the viscosity of injection fluid. Also, we have seen different regimes and phenomena when we use non-Newtonian fluids. Until now, I have published 2 journal papers and I have attended several conferences. That's it. Thank you for your attention.
Thank you, Soheil, for this most interesting presentation. We have a few questions.
Yes.
From Marc-André Fortin. On the slides 10 to 12, could you provide more information about the heavy fluids versus light fluids?
10. Okay, this is the schematic of the setup. We have 2 fluids. One heavy fluid that is injected through this reservoir, and we have a light fluid that is actually inside the outer pipe. And in each experiment, first we fill the outer pipe with the light fluid, and then we start the experiment by opening the gate valve. The heavy fluid comes inside the pipe and remove and displace the light fluid toward the other reservoir.
All right. When you talk about light fluid, is it just water or is it something else?
Yeah, it's pure water. Yes.
Okay. Did this answer your question, Marc-André?
Oui, tout à fait. Mais j'avais une deuxième partie de question.
Oui. Could you explain, Soheil, if the theory of heavy and light fluids you developed could apply to biological fluids, for example, mixture of blood serum and saline water?
Yes, the heavy fluid that I used in this section, this is the non-Newtonian fluid that the blood also follow non-Newtonian rheology. Here I used a viscoplastic fluid. So these are a type of non-Newtonian fluid that is the same the blood. So I think, as I said in the first slide, another application of injection of such fluids is in bioengineering.
Thank you, Soheil, for your answer. C'est tout le temps qu'on a pour les questions ici et pour les conférences des étudiants. Donc, merci à tous les étudiants qui ont présenté ici.